Can STMicro's time-of-flight sensors provide an all-in-one system for an easy, cost-effective, and small-footprint people-counting application? Join me, Todd Baker, as I explore how applications using time-of-flight are rapidly growing in utilization and offer an endless variety of uses across many industries. So, this weekend, my son had a basketball tournament, and obviously we're all trying to stay safe and make sure we got our masks on and they're reduced capacity in the arenas and everything. And, as we're going in there, you're standing in line, you're 6 feet from everybody, and you're just standing in line and you get up and they're about ready to scan your forehead and you're just thinking to yourself, okay, this is it. This is how I find out that I have the bug. And there's that kind of part of you that I think is worrying all of us. And that complexity that's kind of been added into our lives right now, it's still very manual. But I've got to believe there are ways and different technologies and areas that electrical engineers are going to solve and make it a little bit more automated for all of us. And today I want to talk a little bit about that. I'm Todd Baker, Corporate Vice President of Engineering at Future Electronics, based in Austin, Texas. Today I'm talking to John Kvam of STMicro, FAE, in Santa Clara, California. John, thank you very much for joining me. I really appreciate the time.
It's my pleasure. Glad to do it.
So talk to me a little bit, John. So tell me a little bit about your background in with ST, time-of-flight sensors, and just an overall engineering design.
Oh, well, basically I'm old. I've been working with ST parts for years and years and years, and I liked them so much I finally got a job at ST. And that went on for quite a while. And I ended up in the imaging group, and we started building these time-of-flight sensors, and it's been the most fun of my life.
Yeah. So a fairly new technology as far as sensors go. They haven't been around that many years so far. So, so talk to me a little bit about time-of-flight sensors. How do they work? What's the basic technology and idea behind them?
Well, the object is to shoot out a little squirt of light, have that light bounce off a target, your cheek, your body, whatever. And when the light comes back, we stop the stopwatch. Knowing that time, we can divide by 2 and multiply by the speed of light, and you get a distance. So instead of knowing that a person is somewhere out there, you can know that that person is somewhere out there at exactly so many millimeters.
Oh, very nice. And so what kind of range are we looking at typically on a time-of-flight sensor?
Oh, we've got several devices. One goes to about 0.5 meter, one goes up to 4 meters, and there's a couple in between.
Perfect. And what's the minimum on them as well?
Oh, well, they're some of them go down to 1 or 2 centimeters, but the problem with the really, really short distance is light bounces 6 or 7 times. And so that tends to give you the wrong number. So
okay, so you're kind of missing there. Okay.
More than an inch or 2 is about right.
Okay. And then so as far as precision goes, I mean, a lot of applications you need to be down to the millimeter. What kind of precision can you get out of an ST time-of-flight sensor?
In a very inexpensive processor, you're not going to be able to resolve too much. Light travels at 6.7 picoseconds per millimeter, and nothing will go that fast. So we end up with a little statistical process that will give you an accuracy of plus or minus 3%. It's a good way to do it. So a little more at short distances, a little less at the long distances, but that's a rough idea.
Okay. And then so if I'm a design engineer and I'm starting a new design and I know I need the time-of-flight sensor, I've got my microcontroller picked out and everything. What is all of the algorithm existing in the time-of-flight sensor itself? Is that an algorithm I need to run on my MCU to do the calculations, or how does that work in most of the systems that you've worked on?
Of course, the answer is both. Most of the systems, it's all done on the sensor, and you get the answer. If you buy some of our more expensive ones and our newer ones, the raw data is sent to your PC for more advanced manipulation. And those are a little bit better answers, but they take a little more work. In the end, though, it's just an I2C interface, and we'll give you the code. So it's pretty easy to do.
I know when I was an intern in Amarillo, Texas, working on robotic systems inside of a fiberglass plant many years ago. I think it was before there were really a lot of time-of-flight options back then. But we had an enormous robot that was on tracks on the ceiling that would go up and down the fiberglass line, taking 60-pound offs off these machines. And the thing was the size of really a Volkswagen Beetle. Could absolutely take your head off, could completely knock you out. It was like a linebacker coming down the line. But we used to use ultrasonic sensors to make sure that there wasn't a worker or an engineering intern in the way of these things. And so I know a lot of applications look at ultrasonic sensors, and now time of flight's out there. What do you see as the advantage of time of flight over something like an ultrasonic? And what other types of technologies out there and applications do you think that time of flight is absolutely the best in?
Well, the advantage of time of flight is light goes a million times faster than sound. So in theory, you could get an answer much, much quicker. Because we use a slightly statistical process, it not as fast as the absolute speed of light, but it's pretty darn quick. The other thing
Right.
is the light goes out in a very specific pattern. The light goes out with a vertical cavity surface emitting laser. So it goes out in a flash of light that's pretty close to 25 degrees. So if we get an answer back, we know what is in front of the sensor at exactly 25 degrees.
Yeah.
Passive IR and ultrasonic are the other two technologies, but both those technologies have a very, very wide field of view. So you don't know if the sound is coming from the right, the left, in front. You don't know the answer. And you get a very precise answer. Now, one could implement full-on radar. The trouble is full-on radar is very expensive.
Yeah.
You can do time of flight for a couple of bucks and no other circuitry needed. You do need to put it behind a little piece of glass, but that's all you need. So in terms of accuracy versus ease of implementation, time of flight really can't be beat.
Yeah, no question, no question. We've seen and worked with a lot of engineers doing radar, and then obviously that's just cost prohibitive for the vast majority of applications. And even in those applications that absolutely must have a radar, that's certainly an insanely complex design, where we found that very few engineers can even get through it. And I think the other thing that we've seen with ultrasonics that I think time of flight really solves is just from a cost effectiveness standpoint. The time of flights much less expensive than what we've seen for a lot of ultrasonics out there. So some great advantages on that I think are great. What about downsides? Is there any downside really to time of flight? Any places or applications where it's got a little bit of difficulty, or places where maybe flip side of that question where it's best suited?
Well, it's an indoor sensor. What happens is we use a very, very tiny flash of 940 nanometer light. Well, the sun is a really big flash of 940 nanometer light, and it
Yeah.
becomes a signal to noise ratio problem. And a sensor that'll go 4 meters indoors can only go one, maybe a little less outdoors. So sunlight is a problem. That's why 95% of our market is in the cell phone camera autofocus. But outdoors, the normal autofocus algorithm works. Indoors, time of flight works better. So by sharing the application, it's almost perfect.
Right, right. Perfect. So I know you've developed kind of a platform with ST's time of flight sensors in an application to basically detect people movement and people coming in and out of facilities. I know, our headquarters of Future Electronics are in Montreal. We've got normally about 1,000 people in our building. At any given day, lots of conference rooms, lots of offices, cafeteria, audience, a whole auditorium. Being able to track where people are, what rooms are populated, that'd be a huge thing for us. Right now we're in a very weird situation where we've been closed for the last 3 months. We're just opening up literally this week. I think, the building that normally has 1,000 people has, I think, 90 today. But I think a lot of businesses are in that same situation where they've got to figure out, okay, I want to bring my staff back in. I want to start getting everything back to some form of normalcy. I need to track my people. How's your solution work? And talk to me a little bit about what you guys do.
Well, if you put the time of flight sensor right above a door jamb, you could see that a mass of photons went in or out. And the problem is you want to know the direction so you can count the number of people. So one of our sensors, the VL53L1, you have the ability to divide the field of view up into two, and you can take a range on the left side or the inside and one on the outside. And by ping-ponging back before, as the person walks through, you can see him go into one zone and then perhaps into both zones and then come out the other zone, and you add one. If they go the other direction, you subtract one. And it seems to work pretty good. We wrote a video on the did a video on the subject, and was rather well received.
So let's take a look at that video really quickly. Okay, so here's the video that you guys have created for the new platform. to be able to do people counting with the time of flight sensors. So talk to me a little bit about this.
Well, that system right there is our evaluation kit, the one that says out and in, and it's got a great big battery, which you don't really need. But down in the bottom is the sensor right there at the top of the door jamb. Oh, and we've connected that to the system. And as the person walks in or out, we've programmed it to change the LED screen. See how small that sensor is? It's really tiny, and it's pretty neat. That's the
Incredible.
evaluation kit satellite, and that you get that for included, and it's a clever way.
Okay.
What this shows is the inner zone and the outer zone as the person walks through. And normally you're going to get a range of 7 or 8 feet, whatever your door is. And as the person walks through, you're getting in a distance that's closer to 3 feet or 4 feet, depending on how tall the guy is. Watch what happens when he walks in. See? Add 1. Person walks by, they didn't cross both zones, so we didn't add 1. There goes another person. And then, of course, one of the problems is if 2 people come in really close together. That can be a bit of a trick. It's not very accurate. In the video, we separated them off and they show. But there goes a person, didn't fully cross into both zones, so we don't count him. And then as he brings a chair in, we only count him as 1. And because the door does not go into the outer zone, we don't count it either. And as the person walks by, again, didn't cross in both zones. And later we'll cancel the meeting because all our meetings always get canceled about the time they all show up, and out everybody goes.
Right. Okay. Okay. And so at this point, it's tracking everybody out down to 2, 1.
And notice the chair didn't count because that's 1 lump of photons. And the good news is you don't see the chair. But if 2 people to hold hands walking through, unfortunately, we'd only count them as 1.
So that's really cool. So, I mean, as far as the design win and exactly how you guys did, how does the algorithm for that work exactly? I mean, we kind of walked through it. So it's basically just looking at photons across the 2 sensors and just saying, okay, I've got photons on this side, I've got photons on this side. So I'm going to go ahead and add 1, and then the same way as they go the other direction.
Right. And you could do it with 2 sensors, but because of the unique nature of that particular one I used, it has a lens on it. And the lens tells us that we can see from where the photons come. So we can divide the field of view into 2 halves. So instead of getting 127-degree field of view, we've got 2 field of view about half each. And so we can see as a person walks into one zone and then crosses to the other zone. So you can
very cool. Okay.
pretty much do all that for a $2-3 chip.
Okay, very cool. And I mean, the applications for that are myriad. I mean, if you do something like that for just counting people walking through a doorway, I've got to believe there's a lot of other really cool applications and things that are coming from engineers to kind of be able to use a low cost sensor and an application to make their device able to interact with the rest of the world around them, which should be a very cool thing. What was the most challenging part of the design as you were kind of working on it? What were some of the things that were really tough, just in general for this application or in working with the time of flight sensor itself?
Well, it's the door. We put that sensor on the outside and the door opened in. And because of that, the door didn't interfere. But the first real life application that wanted to do with this, they wanted to put it in a hotel room. And of course, all the hotel rooms, the door opens in. And that's still a challenge that we haven't quite figured out. But what we have decided is the sensor works just as well if you mount it on the wall looking sideways. Works the same way as a person walks back and forth. And it turns out that the thermostat for this particular hotel happened to be exactly there. And darned if some thermostats don't have power and communication. So we were able to solve that problem pretty cleverly. The other problem is my facilities people really didn't like me messing with their doorway.
Yeah, we always get in trouble with that, don't we?
Oh, yeah.
It's there's always something that always makes some trouble. I wonder if you could, with that, you've obviously got an ST microcontroller, I'm sure, collecting the data and making the decision to count. So I wonder if you couldn't add, an additional sensor, maybe a Hall effect sensor, something like that on the door itself to detect the door is moved. And so maybe we remove that as the door is moving. It'd be interesting to it would be interesting to see if there are some ways of figuring that out with maybe some additional design. It's got to be something that you could do on there.
Yes.
I'm sorry. Go ahead.
ST makes an accelerometer that you could put on the door. You could
There you
even put it
go.
on the door jamb, and as the door opens, there'd be enough vibration to do that. Somebody thought a pressure sensor would work so that as the pressure inside and outside of the room would change as the door. They tried that. There's no end to the number of possibilities. And you're right, Hall effect sensors are easy, but somebody decided that since the door was going to open up underneath the time of flight, if there was a little flange on the door, the time of flight could see that flange and say, okay, the door is closed. So
Right.
there's
Okay.
many,
Okay.
many possibilities.
Very cool. Well, that's definitely interesting. That's half the fun of engineering is figuring out the problems and the solutions. And it seems like every solution brings another problem, but that's what we enjoy to do. That's why we got into this, right? So, so you talked about the reference design. So is that reference design fully available to customers or designers that want to look at it?
If you go on to the ST website and look up the VL53L1, eventually you'll get to the code. It's on there, and you can download the code. You can implement it on that particular evaluation kit, which is only a few dollars, and you can be installing and running exactly like I show in the movie in a couple of minutes. Well,
Yeah.
let's call it an hour or two.
Beautiful. And I'm assuming since you've got the code, you could also take that same application, modify the code to whatever you're trying to do for your personal application or whatever your design may be. And a lot of that work might be done for you to make modification of the design pretty simple for design engineers that are out there and might be inclined to do that.
So the ST Imaging Group we don't sell software. We don't sell parts. And so we publish all the software. You just download it from the website and you too can be right up there researching with us.
Beautiful. The easier to design, the better. If you're an engineer like me, that's always what I'm looking for is maximizing efficiency. So that's certainly important. So what do you guys think that your time of flight sensors, ST's time of flight sensors, bring to the table to make the design easier for engineers to work with? What are the things that you guys think you do particularly well that no one else out there is really doing?
Well, instead of sending you a register map and making you read it and figure out what everything does, we give you the code. It runs on any C processor. You implement the I2C interface to whatever processor you've got. I'd like to think you'd buy an STM32, but no rules. And you could implement it in your design no matter what you happen to have. And that flexibility is probably the best thing that ST brings to the table.
Makes a lot of sense. Yeah, and that's huge. I think that's one of the differentiators out there today is, making software available so you're not having to write your own code from scratch. I think things have come so far in the last 15 years, or more, making it so much easier for designers to use these products that are out there. So, like I said at the beginning of our conversation, I think there's a lot of technologies out there. There's a lot of cool things in applications that are going to be needed, as the world is changing. What are some of the other areas that, sensor areas or technology areas that ST's in, do you think are really interesting and are going to help with applications for people tracking, for, any kind of COVID monitoring, for any kind of contract tracing, things along those lines? Anything that you're really excited about?
Well, the time of flight sensor can be used to turn on a red LED when you get too close to me, and we can set that up for 6 feet if that's what you want. We can use the same sensor in a very short distance mode so that when you bring your finger and touch a button or come close to a button, you don't have to touch it. It would be a touchless button. You could do that. You could do, there is wireless communication, there's near field communication, there are all sorts of processors and sensors you can do. Boy, the ST website is littered with that stuff, and lots of people are coming up with ideas all the time.
That's beautiful. I think the idea of touchless buttons and things along those lines is absolutely phenomenal. I think, all of us want to interact a little bit less with all the things in our daily lives in many cases, just to, again, try and protect our health and the health of our loved ones. So, I think from that standpoint, that's just a really cool application. Would love to see that really take off. So that's very cool. Well, John, this has been great. I really appreciate you taking the time and kind of walking me through the sensor portfolio and some of the applications that ST has done. If you're looking for help with any of these applications, please feel free to contact Future Electronics. You can contact us at shapingthefuture@futureelectronics.com. We'll get back to you, and we'd be happy to help you with any of your time of flight designs, any of your ST designs, or anything else that you're working on. So, John, again, thank you so much for the time, sir. Have a wonderful day, and we'll talk soon.
You're welcome.